Hello students, and welcome to our first video here for our next topic. We're looking at calculus here, and I know you're thinking we've already done calculus, and you'd be right. We have studied some differentiation before this. Let's go back and have a little look at that. When we had a function and we produced a derivative function from that, right, we differentiated it to produce a function that describes what the gradient of a tangent would be at any point along that original function. Okay, we call it a gradient function perhaps. So that's what our derivative tells us. It tells us what the gradient is at any point along that curve. Now, if I had a straight line, then that has a constant gradient, so the derivative is a constant, like 2 or 5 or -1. If I had a simple quadratic, like y equals x squared, then the gradient of any tangent to that parabola, right, at any point, for any value of x, the gradient of the tangent would be 2 lots of x in that particular case. Now imagine that I had a function where the gradient of a tangent at any point is also equal to the function at that point. So where my function equals 1, the gradient of the tangent equals 1. When my function equals 2, the gradient of the tangent equals 2, and so on. So as my function increases, my gradient increases. As my function decreases, my gradient decreases as well. Now such a function does exist, and it is an exponential function. Y equals e to the power of x, where e is this special number. It's about 2.7, thereabouts. And so y equals 2.7 to the power of x. Right? The derivative of that function is the same as the original function, is y equals e to the x. Now, that is a very important function. We'll use this all of the time and variations on that. This number e is irrational and transcendental like pi, and it means that to write it in exact form, we need some sort of abbreviation. So we use e as that abbreviation. It's Euler's number is where the e comes from, perhaps. Anyhow, it is important to us. You'll find it there on your calculator. You might have wondered what it was in the past. You'll see it there, and we can use our calculator to evaluate things like e itself, or e squared, or 1 over e squared, or whatever. Okay, so just like we have pi there in our calculator that we use for calculating areas and circumferences or something, well, we also have an e there saved in our calculator that we can use for evaluating exponential functions. Right, we can have other exponential functions that have bases other than e, but if I don't specify otherwise, e is so helpful and important to us when I generally refer to an exponential function or the exponential function. Unless otherwise specified, it's going to have a base of e. So here we go. Use the calculator to evaluate this to 3 decimal places, e squared. How do I do that? We'll need to grab the calculator. I've still got this Casio emulator here, which is very similar to the abacus that you're probably using. Now, these buttons are arranged slightly differently, but it's the alpha one that I want here. See, above the alpha there, it's in pink, and above here, this little this 10 to the power of x. Next to the pi, I've got a little pink e. Well, I need to use the alpha button to access any of those pink things. We don't use very many of them, really. We haven't up until now. But alpha, this thing, right, that brings up e. So if I just press equals, it'll give me 2.712, something, 1828. Now I want e squared. There we go, there's the squared button. E squared, what does it equal to? About 7.389. 7.389 is e squared. Is that what I wrote down? 7.389. Whew, I was lucky. Next one up, 1 over e. Let's do that in the calculator. Calculator again. I want to go 1 over. I can use the fraction button if I like, or divided by. Remember alpha here, 1 over e. Right, about 1 over 2.7 should be about 0.368. 3 decimal places, 0.368. There we go. Now this one here, this is a bit funny. E over pi times sine 60. Why on earth would I do that? Well, it's just a random coincidence, really. But if I do that, if I go E over pi, right, times sine 60. Don't forget to close the brackets. What do I get? Ooh, 0.999. Look, it's not a rounding error. It's just an odd sort of a thing. Don't get the idea that it's exactly 1 or anything like that. No. I just wanted a complex calculation there, and that's what it turns out to be. So 0.999. Okay, that's how we use our calculator to evaluate expressions involving e. Much the same way we use our calculator to evaluate expressions involving pi. Now, what about this one here? Why graph the exponential function from -3 to 3? Right, I've got some axes here. Let's chuck some labels on there, an x and a y, and some numbers there. I want to go from -3 to 3, that's fine. And look, if I punch into my calculator, e to the power of 3, I get a number that's about 20. So I need to go up that far. So, let's start with the easy ones. E to the power of 0, anything to the power of 0 equals 1. So you can see there's a dot at 1. E to the power of 1 is e, that's about 2.7. E squared is 7.4-ish, I think. And e cubed is 20 point something. So it's up there. Going back the other way, e to the -1, that's 1 over e, and we saw that was 0.368 or something. So there's that one there. 1 over e squared, or e to the -2, is getting closer to 0, and 1 over e cubed is really fairly close to 0 now. Of course, as I move to the left here, we should recognise that I end up with e to the negative to a large negative number, which is the same as 1 over e to a large number, and that's e to a large number is going to be a very large number, and the reciprocal of that is going to be very small, very close to 0. It's going to be positive, but positive very close to 0. So that's the trend that we see there. That's why we have a horizontal asymptote for our exponential function at the x-axis, or y equals 0. Let's run a smooth line through there. Here we go. We get something a bit like that. That's as smooth as I could draw it on PowerPoint. And a couple of little important points here. When x equals 1, e to the power of 1 is equal to e. So if we run across there from that intersection, that point there would be at e. If I drew a tangent here at the y-intercept, right, the y-intercept occurs at 1. Remember that the derivative of the function is equal to the function. So the gradient of this tangent here is equal to whatever the function is. The function's equal to 1. That means the gradient of this purple line is equal to 1. Doesn't really look like it because I have compressed the vertical axis. But I have a y-intercept of 1. I've got a gradient of 1. That means the equation of that line, I've put my head over the top of it there, the equation of the line is y equals x plus 1. There we go, that's the equation of that straight line, and we'll do some more exercises with that sort of a problem in future exercises. Rightio. Well, that's it. That's our introduction to e. It is an irrational and transcendental number. The exponential function, when differentiated, produces the same value. Now, there is just a little sort of bit of trivia here as much as anything else. Another way, perhaps, to generate e, or to understand e. You've probably studied some compound interest before, certainly should have. And we might remember that our final amount is our principal multiplied by 1 plus the interest rate raised to the power of the number of terms, the number of compounding periods. Well, consider this situation here. If I have $1 invested for 1 year at an interest rate of 100%. Now, if that only compounds annually, then it's a fairly straightforward. I'll earn $1 interest over that year. My final amount would be equal to $2. If that compounded every 6 months, you'll remember what we do is we halve the interest rate and we double the number of terms. If that compounds 3 times a year, I'll have 1/3 of the interest rate and 3 terms, and so on. So I drop a little table here. The number of periods that this is going to compound per year, an expression for how we calculate that, and an approximation perhaps of what the value would be. So if that compounds once a year, I end up with $2. If it compounds twice a year, it's 1 plus a half all squared, gives me $2.25. A little bit more. 3 times a year, it's 1 plus a third to the power of 3. It's $2.37. You can see this climbing up. If that jumped all the way to 1,000, if I compounded that 1,000 times, about 3 times a day, right, then I would end up with a final value of about $2.72. If we push this now, if we look at the limit as n approaches infinity of 1 plus 1 over n to the n, right, we end up with this figure here of about 2.71828, which is E. So we can define E that way, in fact. The limit as n approaches infinity of 1 plus 1 over n to the power of n. That's the most our compound interest could return if we compounded it constantly. Right here. There we go. That's it. That's it for E. Y equals e to the x is the exponential function. E is about 2.1718. And the derivative of e to the x is e to the x. That's all for today. Our next exercise is on transformations of the exponential function. Right, back to some graphs. I'm sure you'll love that. I'll see you then.